Alright, so yeah, we were talking about what do you call the surface of the sun? Well, they decide to call the surface of the sun the point where you can't see through it, or the point where it becomes opaque. Alright, it's kind of like a cloud. A cloud up in the sky, well, you can't see through it if it's a thick enough cloud, but you could fly right through it. It doesn't matter, it's not going to stop you, it's not solid. Okay? But you can say there's a surface to the cloud, that's the point where you can't see through it. That's what we do with the sun too. We say, okay, the point where we can't see through it anymore, that is what we consider the surface of the sun. So the sun's atmosphere also has three layers, so don't get them confused with the interior. The outermost layer we call the photosphere. Also called the photon sphere, we just leave the N out. The photosphere has the temperature of 5,800 degrees Kelvin. This is what we talk about when we say, the surface is the sun. This is where most of the photons, the light coming from the sun, is emitted at this temperature. And that's the one that has the black body curve that peaks right at the middle of the visible spectrum. Within the photosphere, we see a couple effects. We see granulation, which is the grainy appearance you see here, the dark and light spots on the sun. And this is caused by the convective cells. The tops of the convection of the hot gas coming up and then the cooler gas going back down again. What we also see in the atmosphere of the sun is we see sunspots. Alright, this is a group of sunspots. We're going to talk about sunspots for a little while. So sunspots, as you notice, they have a darker region, and they always seem to come in pairs or groups. There's a reason for that. And then they have this outer region that's not quite as dark. Just like with shadows, we call them the same thing. This outer region is the penumbra. The inner region, the inner dark region, is called the umbra. And the reason they come in groups is that the sunspots have a magnetic field between them. One of them will have a north pole, one of them will have a south pole. And you can't have a magnet unless you have both poles. You have to have a north and a south pole. And so that's why we see them in pairs or groups, is because it's the magnetic field popping through the surface of the sun. These are cooler regions. Their temperature is around 4,500 degrees Kelvin. Notice that the photosphere is 5,800, so that's 1,000 degrees cooler, so it appears dark. Now it is giving off light, but relative to this part, it's not giving off as much light. But if you just isolate there, it would give off light at about 4,500 degrees. So it's just cooler gas. Yeah. And the number of sunspots varies. We can have times when there's a lot of sunspots. And then there's times when there's no sunspots at all. So we have what's called the sunspot cycle. And this is an 11-year cycle. Every 11 years we have a sunspot maximum, and then we go into a sunspot minimum, and then back to a maximum, and so on, every 11 years. And as far as we know, this has been going on indefinitely. Here's a plot since 1870, and it shows every 11 years there's a peak. Okay? So AA, we'll talk about that in a second, but this is the number of sunspots, is the yellow one here. Okay? And notice it peaks, and sometimes the peak is a lot higher, and sometimes it's lower. Okay? Why? We're not exactly sure about that. There are a lot of people that try to predict it, but it's hard to tell. This one goes even further. This goes back to 1750. Okay? So they've been watching sunspots for a long time, but they still see the 11-year cycle. Notice that down here in the 1800s, the early 1800s, even the maximum, still had 11-year cycle, but the maximum was less than it normally was. During that time, there was not as much energy coming from the sun, and the Earth actually went through a cooling phase. A mini ice age. It didn't last about 20, 30 years, but it was enough to actually affect crops and climates, especially in northern Europe. There was a lot of famine going on. because they weren't able to grow crops because it didn't warm up as soon in the summer, or some places, even up in Norway and Sweden, ice that was on the lakes and stuff never actually melted that summer when it usually would, because it was cooler at that time. And this has a name, climatologists call this the Maunder minimum. But then it came back and it started going up, and then the sun got very active here in the 1950s and 1960s. All right, so what's that mean for now? Well, let's look at our current rate. So this is, see the cycles, this one hit around 1990 was the peak right here. And then we had our minimum, the next one 11 years later hit around 2001. And the last peak was about 2012, actually it was pushing 2013, it was a little later than that. And notice the same thing, back in the 1990s the sun was much more active, and then we came down to minimum. In fact, this minimum here, between 2008 and 2009, was the lowest minimum ever recorded, meaning we went for the longest period without any sunspots at all. They just kind of completely disappeared for a while. And then it came up here, and I haven't put the latest data on, this ends at about 2015, but it did follow this curve. It's coming down, and you see we're down here in this part of the peak here. And so 2020, we're heading into the minimum right now, and it's going to jump back up again because the next peak, remember, this is about 2012, 2013, kind of halfway between here. 11 years from now is 2024. It's going to peak again. The question is this going to be a peak way high, or is this going to be a low peak? There's a good thing when it's a low peak, because the higher the peak, actually the more energy that the Earth gets, and it heats up the Earth. So, we're worried about global warming. Well, the sun is actually helping us out. Just by luck, the sun didn't put out as much energy this last cycle, and so that reduces the amount of energy, so that reduces the amount of global warming. If the sun all of a sudden gets very active, and we keep putting out all these gases, greenhouse gases, then the effect is going to be increased dramatically. So the question is it's a very complicated cycle. It's not just our atmosphere. It's also the atmosphere and the sun and what we call the space environment, or the space weather environment, the interaction of those. All right. So that is the sunspot cycle. We are currently in the minimum right here. We're hitting the minimum. You notice it comes down slower and then it goes up very fast. So in the minimum will be 2020 through 2021, and then I'll start up quickly in the next maximum. All right, the next layer of the sun's atmosphere is part 2. This is the chromosphere. And this has a temperature of around 30,000 degrees Kelvin. So it's very much hotter than the photosphere. And usually you kind of see it as a thin red layer above the surface. You see how the surface is down here, there's kind of a black line between that? That's the photosphere, but this glowing red gas here is very thin, but it's above the surface. It's kind of hovering above the surface. And it's much hotter gas. The reason we think it's hotter has to do with the magnetic field of the sun. The magnetic field of the sun is actually pumping energy into this gas and keeping it hotter. Okay? But we see effects like this. See this? This is a prominence. So under the chromosphere we see prominences. Here is the prominence, and what this is right here, this is a sunspot, this is a sunspot. Remember I told you that there's this magnetic field that goes between the sunspots. Well, a prominence occurs whenever you get gas right here, gas trapped in this magnetic field. So the gas gets trapped in the magnetic field around the sun. So prominences are gas trapped in magnetic field between sunspots. Now those prominences can just hang out there like that and just look like this And they can just hang out for a couple months and then just fade away. As the sunspots, because sunspots come and go too. And the sunspots can last for a certain amount of time and then they just start to fade away. So these prominences can come and go. But they don't always come and go. So if I'm doing it on my picture here where these are sunspots, right? There's sunspots here. The prominences now are the gas trapped in here because the gas has a charge. Most of it is hydrogen. Hydrogen is just a proton. That proton has a positive charge. It gets trapped in the magnetic field. And here's some more prominences. This one was a special, this is from the TRACE spacecraft, which is a spacecraft put up in space just to study the sun's magnetic field. And you can see you can trace the magnetic field lines of the sun. And we try to make a nice simple rainbow shape. But the truth is it's actually very, very complicated. And the sun's magnetic field gets very complicated at times. Here is a huge prominence off the side here. Remember, the Earth is about a dot, about this big as the size of the Earth. So relative to that, this is a whole lot of gas and energy trapped in the sunspots, in the magnetic field above the sunspot. That was a very, very large prominence. They usually aren't that big. Oops. Here is another one, and they give you the size of the Earth here too. So prominences are very common. In fact, they're common, most common, when we have a lot of sunspots. So when we're near sunspot maximum, you see lots of prominences. At sunspot minimum, you see none, because they have to have sunspots for these to occur. Then we can also get, I'm running out of room.